Hello everyone, welcome to the course on architectural design of ICs. So, in the last class we are seeing this low power design tips. So, initially we have discussed why we need to consider about this power consumption in VLSI circuit design, and then what are there actually the sources, so the power consumption sources are there in digital CMOS design. So, we have already seen that there are two type of power, one is the dynamic power, another one is the static power. In dynamic power you are having two type of power, one is this switching power and another one is this the internal power, and in static power you are having the leakage power. So, now we will see that the corresponding equation for dynamic power. So, as we have already discussed that dynamic power is the sum of the switching power and the internal power. So, if I just write that equation in the equation form, if I just write, then P d, the dynamic power consumption, will be the P s is the switching power plus this P I is the internal power. So, the switching power I can write, that is C V square F, and the Pi is V into ISC. ISC is the short circuit current. So, the total power will be C effective star voltage square into F switching. Why? Mainly actually this particular contribution of this internal power is very much low in compared to the dynamic power the contribution to the overall dynamic power consumption. So, that is why it is not equal. You can write that as this is the major contribution. So, that is why you can just omit this particular term. This will be in, let us say, in nanowatt, whether this would be in milliwatt, switching power should be in the range of milliwatt. Okay. So, this actually this short circuit current is basically whenever you are having this ground to this power to ground one connection for a short time. So, which creates this short circuit current, and because of that short circuit current you will get this voltage into short circuit current as the internal power source. Then the static power. The static power consumes due to non-ideal characteristic of the transistor that leakage can be taken place. Static power is nothing but leakage power, and there are two main types of leakage and their subsidiaries. What is that? That is I off and I gate. Then what is this I off? Is that is the subthreshold leakage or this drain leakage current. This I off basically mainly depends on the contribution of this I d weak, which is the subthreshold drain current, I inward, which is this reverse bias current, and IGIDL, which is gate induced drain leakage. So, all these currents are basically, if you know more about the CMOS device. Okay. So, at that time you might be actually the semiconductor device. If you know, then you will be finding that okay, these are the, that means the currents which are already there as we are choosing the VLSI circuit design on CMOS technology. So, whenever we are basically reducing the that means the gate length by actually day by day to let us say nowadays 3 nanometer people are trying. So, whenever we are reducing this particular gate channel length, so this these particular terms are becoming dominant day by day. Okay. So, then the other power consumptions, actually the other power consumption is that this gate leakage current, which actually happens because of this I tunnel, which is nothing but the gate tunneling, and IHC, which is the hot carrier injection. So, all these are because of the properties of this CMOS device what we have chosen for VLSI circuit design. So, if I just actually make the chart, so then I leakage, it is having I off plus I gate. Okay. So, I off contributes is the summation of the contribution from I inverter reverse bias current, I d weak, that is the subthreshold drain current, and then IGIDL gate induced drain leakage current. Then the I gate current is basically the tunneling current, gate tunneling current, and the hot carrier injection current. So, actually what happens is that because of this at the gate level we are getting this ID weak, which is the subthreshold current. Then at the gate again this in this particular direction the tunneling is happening. So, because of that this we will get this gate tunneling current, and then we will get because of this actually body we will get one current consumption which is nothing but this IGIDL, gate induced drain leakage current, and then we will having this I inverter which is this reverse bias current, and then we are also having IHC which is the hot carrier injection current. So, all of this actually contributes to the nothing but the I leakage. So, the power consumption will be the voltage into I leakage. So, in this I leakage which is the contribution of several other, that means the contribution from this reverse bias current or this GIDL or HC or this I in that means reverse bias current. So, because of this technology scaling, this I leakage is becoming more and more day by day. So, which consumes this leakage power consumption to be a major concern which we should consider while we will design our system. Okay. So, then there are other actually various power. One of the power is that metastability. So, output of the flops remains on the undefined state which is caused by the violation of setup and hold. So, we know what is the setup and hold, and in digital systems when we can get this metastable state, that also we have already seen. Okay. So, that means if we get one metastable state in any digital circuit design, so at that time it can create a lot of power consumption into the circuit. Then actually we will be having this glitches. Glitches are the unwanted or undesired changes in signal which are resilient or self correcting, caused by the delays in lines and the propagation delay of the cells. That means, the delay actually this glitch, we have already seen glitch, how we can actually because of the delay of the gate or delay of the net between two, if two signals are basically arrives at the gate inputs at different times. So, at that time they may cause some of the glitch. So, glitch in actually in a digital VLSI system design, that is not at all appreciable, because we have already seen that in case of the what type of hazards we are having or we can get whenever we do this logical optimization or something like or this gate level optimization. So, at that time we can get these glitches which can cause or which can totally destroy the circuit's performance very badly. So, that is why this glitch also contributes some of the power consumption in the overall power consumption of your circuit design. So, then the latch ups is a short circuit path between the supply and the ground. Okay. So, these latch ups are basically what we consider as the internal power. So, this is the contribution from the, it will if latch up happens. So, at that time it will contribute to the internal power of your system design. So, the power estimation mostly based on the tech libraries. Okay. That means, how the EDA tool, suppose in EDA tool how they calculate the or how they estimate the power, mostly it is based on the technology library and based on two major calculation. One is this activity and the second one is the probability. So, what is this activity? Activity is the number of toggles per clock cycles on the signals and averaged over many cycles. Then the probability is the percentage of the time that the signals will be high. So, based on these two approaches, actually this activity as well as this probability, they calculates the overall power consumption of your total circuit. And in actually this is the rough estimation which has been done on the beforehand, but in actual power consumption which is happened whenever you will develop the IC or you will get the IC, in the physical form. Okay. So, suppose here we are having one clock signals of period, let us say 10 nanoseconds, and we are having two signals N1 and N2. So, at that time we have to, that means set the activity as that, okay, the number of toggles per clock cycles on the signals. So, the number of toggles means this N2 is basically toggling 2 times, okay, and then actually the probability is the percentage of the time that the signals will be high, okay. And then here activity is for N1 signals, what is the activity, that means how many, for how many clock cycles it is toggling, that we have to check. Then depending on this particular equation, now we can calculate, or the tool basically calculates the rough estimation about the power consumption. Okay. So, this is how in EDA tool basically does the power consumption. Then actually whenever we got the information about the power consumption, then we have to also be think about the power reduction technique. So, why I have already discussed, or I have already told that I need to be actually design the circuit in such a way, so that the power consumption should be lower and the device can run for a very longer time, or the system design which we have designed, that is much more beneficial to the users. Whenever we do any or design any system, that will be actually we design the system intended towards the users. So, whenever the users will be benefited by reducing the power, or they can get the benefit in terms of their electricity bill, or they can run, that means for a longer time the device, once they charge and then they can run for longer time. So, that type of device we should be focus on for designing. So, that is why we have to know, once I know that okay, this is the power consumption of my circuit. So, at that time can I basically reduce the power consumption. So, what are the things we have to know for reducing the power. So, power reduction techniques is very much important and can be classified into 3 main categories based on their implementation and occurrence. What are they? The device engineering, the circuit engineering and the system engineering. So, the device engineering means actually the what we can say is that in VLSI design flow, actually you are having this, let us say this physical layout, and then you will be having this gate in, that means gate level information, you will be having that this device level information. So, every of this level, transistor level, then the device level. So, every of this level you can apply the power reduction technique. So, that is why this in device engineering also how we can apply the, that is power reduction technique. This refers to the technique that are implemented on the underlying transistors that form digital circuitry. This is mostly involved with the transistor level components. Okay. So, the transistor itself, because as you can see that transistor itself, it is having so many power factors like this IG ideal, then ISC, IHC, I inverter. So, these are the, so if you can improve the device performance, okay, so then at that time that particular power reduction you can do, or power, that low power you can do, that means the leakage power reduction you can do. Then the circuit engineering, not only leakage power, the main, the sort, that means the switching power also you can do while you are working with the device level engineering. Then the circuit engineering refers to the techniques that are applied to gate level or logic level, which are clusters of transistor that performs a small computation like NAND, NOR, etc. That means, while you are designing this basic cell or the standard cell, if I say, so at that time you can apply this circuit engineering, or you can apply the low power techniques to make. So, the lower level, if you can achieve the power reduction, let us say by factor of x, and those transistors or those gates will be used in your main system for million times or 1000 times or 10,000 times. So, 10,000 times advantage you will get while you are basically reducing the power at the device level or at the circuit level. Okay. So, and you will go up in the VLSI design flow. So, the more actually this less reduction you can achieve in system design, sorry, in power consumption. Then in system engineering, these are referring to the techniques that can apply to the macro blocks that are the part of a big data path or microchips. So, for the like whatever actually we are seeing, that architectural optimization of each of these blocks, let us say adder, then the multiplier, then the divider, then this codic block, then the FFT block. So, all are basically intended that architectural changes, these are like micro, that means the macro blocks, okay, bigger blocks. So, there also we can change something, some architectural changes or some, that means logic level changes to make that thing for useful for low power application. So, other actually the low power techniques, there are several techniques to achieve this low power. Is that one of this, that means major techniques we use is that parallelism and pipelined micro architecture. Then there are clock gating options, there are power gating options, there are voltage islands, there are gate sizing, there are multi VDD approach, there are this DVFS, dynamic voltage frequency scaling, and in device level you will be having this multi threshold device, low capacitance in device and high KHF based MOS. That means, not only this generic CMOS with high K of actually the CMOS device, at that time it will be changed to reduce the corresponding circuit, that means to reduce the corresponding power at the device level. So, if we can use or if we can reduce the power at the device level, means what, we can achieve the power consumption advantage in a bigger way, rather than we are doing the at the top level, which is the system level optimization for the power. Okay. So, then this this multi VDD or this gate sizing, these are the circuit level actually this power reduction techniques, whereas this parallelism pipelined, so the, or the clock gating, these are the system level power reduction technique that we can apply. So, then dynamic power reduction. Dynamic power reduction is very much important because the clock tree path consumes more than 50% of dynamic power consumption, and power consumption by combinational logic whose values are changing on each clock edge, power consumed by flops, power consumed by the clock buffer tree. Asynchronous logic circuit which is not driven by the global clock is also changing due to the state changes in the flops. So, all these are basically the source of dynamic power. Now, one point is that clock tree consumes more than 50% of the overall dynamic power contribution. Why? Because the power is basically distributed throughout your entire chip, okay? And this clock tree is one of the, that means path which will be that means active for all the time inside your chip, because clock is continuous to your system. Okay. So, continuous system means it will be continuously supplying the corresponding clock signals to the all the sequential element in your circuit. So, that is why, so clock signal means what, depending on the, that means frequency we have chosen, sometimes it is 1, sometimes it is 0, sometimes it is 1, sometimes it is 0. So, there is switching, continuous switching in the clock signals, and it is basically supplied to the, that means it is supplied to the clock tree network is distributed throughout your entire chip. So, obviously, it will create, it will consumes more power, dynamic power. So, that is why this statement it is that it is written as the 50% of the dynamic power consumption because consumes because of the clock tree buffers, sorry, clock tree synthesis. And then some of the combinational logic, if you are actually if you run the combinational logic. So, at that time combinational logic means what, whenever the inputs are available at the, that means input end, immediately the output changes its behavior. Okay. The state the output, depending on the logic, the output state changes. Okay. So, which again creates the switching very fast in combinational circuit, but whereas these flip flops, they has to wait for the clock. So, when the clock edge occurs, then only it actually switches the data, otherwise it remains silent or it remains idle. So, but the every flip flops and this clock tree buffer, they also consumes the power, which contributes to the overall dynamic power consumption of the circuit. So, then one of the major technique to reduce this power consumption is this clock gating. So, what I say is that that dynamic power consumption clock tree synthesis is the major contribution of overall switching power. So, that is why if we can kill the switching, that all the time actually though the circuit is in the idle mode, but still I am supplying the power, which is unnecessarily consuming the power. So, that is why to kill that, if we use the circuit technology which is named as this clock gating means what? Whenever I need, that means the device is in idle state, the clock is also idle, the device is in an active state, the clock is active. So, that means every of the clock signals of the sequential element, now they will be gated with one enable signals. The clock will be now enabled, which is known as this gated clock. So, the major clock gating is the major dynamic power reduction technique, as we can reduce the clock tree, say that means clock tree power consumption to a great extent, that means we will obviously we can reduce the dynamic power consumption to a great extent and get the clock as much as the flip flop, which is not necessary to be toggled. Otherwise, in every clock cycles flop will toggle and dissipate more power. Local clock gating has a new enable to every flip flop where clock gating is necessary, but with complex VLSI design, it is not sustainable to use local clock gating. We need to derive a logic for new enable with the current logic. So, sometimes what happens is that you can actually do this local clock gating. Local clock gating means some of the sub blocks also you can do the clock gating locally, to that means place them in the dormant mode whenever they are not functioning. So, but in present days, that means complex VLSI circuit design, it is very much hard to find out those blocks and then again do the local clock gating. Okay. So, that is why it is not that much easy. It is not that you cannot do, it is impossible to do, but that is not that much easy. So, if you can identify and then you can just do the local clock gating, then you will get the advantage in the overall dynamic power consumption. Okay. So, what is this local clock gating is that local enable is used to gate the flop, and enable and clocks are AND gate and the gated clock is provided to the flop. Local enable do not have global perception. That means what? This particular enable signal will be actually enable signals, when this enable signal will come. This enable signal will come depending on the corresponding. Let us consider one particular example, that suppose we are having one let us say one this system on chip which is having this let us say this video processor as well as the audio processor, that means video processing block, audio processing block, and then we are having some let us say this other processing blocks. So, if one condition applies, that whenever this video processing block is working, at that time the audio processing block that may not be active. So, at that time I will not activate. Suppose we are using only the video, we are focusing only, or we are working on the video processing blocks. We do not need to activate the audio processing, or it will be never used whenever I use video processor. So, at that time I will be never using the audio processor block. So, at that time instead of using this audio processing block, that means inside of the chip what will happen, as the power supply is already, or the clock or everything is already there. So, it will be also activate and it will contribute some of the power consumption to the overall dynamic power consumption. So, at that time what will I will use, I can say that okay, for this particular condition whenever I will use video processor. So, at that time you kill or you shut down the total audio processor block. So, that the power consumption becomes very much minimal at that time, because we have. So, at that time this local enable signal will be activated whenever I put this condition that okay, whenever I will use video processor. So, at that time you please stop the clock connections to all the blocks which are available in audio processor. So, this is just one example. It is not that whenever I will use video processor, so at that time I have to I have to stop the audio processing. It may happen. So, that is the example of local clock gating. So, this is how actually we do the local clock gating in digital circuit design. Okay. So, at that time the enable signal will be local, it is not, it will be not globally, or it will not be the enable signal which we have used in the our top module block or the main module block. Okay. So, this clock gating is one of the technique which is majorly used for dynamic power consumption reduction. Later on again we will see what are there the other techniques to reduce the power consumption. So, thank you for today's class.